Section 5.5 is on z-scores. In the last lesson we learned a little bit about normal distribution, and we were basically given a mean and standard deviation for which we labeled a normal distribution curve. We labeled the first, second and third standard deviation above and below the mean, and we had certain percentages associated with those labels. Between the first, within one standard deviation, 68% of the data; within two standard deviations was 95% of the data; and within three standard deviations was 99.7% of the data. But sometimes you're given a value, like the candy cane example in section 5.4, where we're asked how many candy canes or what percentage of the data was longer than 20.68 centimeters, but that wasn't one of the labels on our normal distribution curve. So z-scores come into play to help us figure out the data, percentages of data, when the values that we're using aren't exactly 1, 2, or 3 standard deviations away from the mean. And a z-score is basically a standardized value that indicates the number of standard deviations a data value is from the mean. It indicates the position of a data value on a standard normal curve, and a standard normal curve has it's a normal distribution curve with a mean of 0 and a standard deviation of 1. If the data value is 2 standard deviations below the mean, it would have a z-score of -2. If it was 2 standard deviations above the mean, it would have +2. If it was 3 standard deviations above the mean, it would have a z-score of +3, and so on. So the best way to kind of get used to z-scores and how they work is to do samples. But before we can do that, we need to know how to calculate a z-score. And with z-scores, they're either going to be positive or negative values, and the positive z-score indicates that it is a data value that lies above the mean, and negative z-score indicates that that particular data value lies below the mean. The z-score formula is something you will be given this formula on a test, but you will need to know how to use it. It's not going to actually be labeled, this is the z-score formula. So you will just see z equals x minus the mean over the standard deviation. So x is the particular data value you're talking about. This little symbol here means is another symbol that we use for the mean, and this symbol here, you're familiar with already, is used for standard deviation. So a normal distribution curve that uses z-scores looks like this one right here. And basically your mean would be at position 0, and then 1 would be 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean. And -1 would be 1 below the mean, 2 standard deviations would be below the mean would be -2, and 3 standard deviations below the mean would be -3, z-score of -3. And this line here just basically has it described in terms of mean. So this one would be mean, of course, in the middle, mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations, and the same for the negative direction. Mean subtract 1 standard deviation, subtract 2 standard deviations, and subtract 3 standard deviations. So z-scores can be used to help compare data from different normal distributions by converting the distributions to the standard normal distribution. So basically what that means is that when you've got all this data, they each have their own mean and their own standard deviation, and it's kind of hard to compare them. So if you all kind of compare them to the same type of normal distribution where the means are considered 0, and then the standard, you're just talking about its distance of standard deviations 1, 2, 3, -1, -2, 3 from the mean, and kind of compare them all to the same set, it's a little bit easier to see which one is better, which data is better, or which data has better results, or not as good results, or whatever you're interested in. Alright, so the first one here says the heights in centimeters of 5 members of the HHM basketball team are 176, 188, 195, 196, and 210. If the mean height is 193 centimeters and the standard deviation is 11, calculate the z-score for the tallest player. So the mean is 193, standard deviation is 11, and you're looking for the tallest z-score for the tallest player. So the tallest player would be, that would mean that your data value is 210 centimeters. So your z-score for 210 would be, according to the formula, it's the data value, which in this case is 210, minus the mean, which is 193, divided by the standard deviation, which is 11. So when you calculate that, 210, subtract 193, divide it by 11, that gives you 17 over 11, which is equal to 1.545, so on. So that we round that to 2 decimal places, that will be 1.55. And the shortest player, in this case the shortest player out of the list we have there is 176 centimeters. So x would be 176. And again, if we go to our z-score formula, I probably should write out that formula again. It's x minus the mean over the standard deviation, which is 176, minus the mean, which was 193, divided by the standard deviation was 11. So 176 minus 193 is negative 17 over 11, which is negative 1.5. It's going to be the same as the other one, but negative 1.55. So the positive z-score for the tallest player indicates that that's 1.55 standard deviations above the mean value, and the shortest player has a negative z-score, which means that's 1.55 standard deviations below the mean. Excuse me. Okay. So the second question says, on her first math test, Susan scored 70%. The mean class score was 65% with a standard deviation of 4%. On her second test, she received 76%, and the mean class score was 73% with a standard deviation of 10%. On which test did Susan perform better with respect to the rest of her class? So z-scores can help us answer this question. So we look at the first test. We've got a z-score of, for that first test, would be, again, our formula, I'll just write it out again, just to remind you what it is. It's the data value minus the mean over the standard deviation. So in this case, the z-score, the data value for the first test is 70, minus the mean was 65, over the standard deviation was 4. So that works out to be 5 over 4, or 1.25. But the second test, if we look at the z-score for that one, and you already got the formula there, so I'm not going to write that out again. It's the data value for the second test was 76, minus the mean was 73 this time, all over the standard deviation of 10. So that gives you 3 over 10, or 0.3. So when you're comparing, like in these particular examples, there's 2 different means, 2 different standard deviations, 2 different test scores. But when you look at in terms of relativity to the rest of the class, this one here, if you look at kind of a standard deviation, not a very good curve, a little bit too curvy on the end there. If you look at the standard deviation kind of as a normal curve, your mean is in the middle here. And this one, the first test is like 1.25, say, so somewhere up around here. But then the second test is 0.3, which is not very much above the mean itself, because this would be 0 and this would be 0.3, for example, and 1.25 would be above that. So if you kind of look at it in terms of that way, you would see that the second test is, she didn't perform as well on the second test relative to the rest of the class, but the first test, she was 1.25 standard deviations above the mean, so she was higher than the mean, and much higher than the mean compared to the second test, whereas the second test she was closer to the mean. So this one she performed better, since the z-score was larger, higher in terms of performed better, since the z-score was a positive and higher than the other test. Okay, the next example, Sally has a height of 1.75 and lives in a city where the average height is 1.6 meters and the standard deviation is 0.2 meters. Leah is 1.80 meters and lives in a city where the average height is 1.70 meters and the standard deviation is 0.15 meters. Which of the two is considered taller compared to their fellow citizens? And explain. So again, you can use z-scores because again, you got different data values, different means, different standard deviations. So what does all mean? So let's look at it in terms of z-scores. So the first one, for Sally, we'll say, Sally's z-score would be, her data value is 1.75 and the average is 1.60 over the standard deviation is 0.20. So if we calculate that, 1.75 minus 1.60 and then divide that by 0.20, we get 0.15 divided by 0.20, which is 0.75. So then if we compare it to Leah's data values, her results, you get Leah, her data value would be 1.80 and the mean is 1.70 and the standard deviation is 0.15. So this is 0.10 over 0.15, which is 0.6666, so on. So that's approximately 0.67 if we round it to 2 decimal places. So relative to the rest of their fellow citizens, Sally would be considered taller because her z-score is larger. Sally is taller compared to her fellow citizens. Because she's higher, much higher, or a little bit higher, higher above the mean. 0.75, a z-score 0.75 would be a bit higher on the standard normal curve. Here would be 0. And say if this was 0.67, then this would be 0.75. So 0.75 would be a little bit higher than the mean then. 0.67 would be. Okay, question number 3. The humidity observed in the morning on the same day in Chicago and Orlando is shown. Assume the data is normally distributed. So if you have to, first question is to determine the z-score for each city's humidity. For Chicago, we would have the z-score is, the data value is 85 minus the average humidity for Chicago is 82 over a standard deviation of 12, which would be 3 over 12, which would be 0.25. So again, it's above the mean because it's a positive z-score. Orlando would have a z-score of, data value is 94, subtract the average humidity is 91, over the standard deviation is 15, so that would be 3 over 15, or 0.20. So when you compare those, so question A was just actually calculate the z-scores, but they're both above, they both have positive z-scores, so it means they're both above the mean. And in question B, though, it says which city has the highest relative humidity, and again that would be Chicago, since it has a higher z-score. So when you look at the data there, the higher z-score, when you're comparing them both to the same normal distribution, standard normal curve, then Chicago has a little bit higher z-score than Orlando, and that would mean that it would be a little bit higher than average relative humidity in terms of its relative humidity. I'm sorry. So there are also some questions where if you're given, you might not be asked specifically to find the z-score, maybe you're given the z-score and asked to find out the original data value or something, because basically you've got, in the formula for the z-score formula, you've got z equals x minus the mean over data value minus the mean over the standard deviation. And those are basically 4 things you have to fill into the formula. So if you have any 3 of those, you can figure out the 4th one or the missing one. So the first example says, here the average mark on Mr. Simon's science exam was 68% and the standard deviation was 11%. Marks were normally distributed, so that's key to being able to use z-scores. And AJ's z-score was negative 2.5. Then what was his actual mark on the exam? So if we look at the formula and fill in what we know, okay, so we know my symbol for standard deviation is not very good. Okay, so we know that his z-score is negative 2.5. We don't know his actual mark on the exam, but we do know the mean was 68 and we do know the standard deviation was 11. So we can either multiply both sides by 11 now to get rid of the fraction, or we can cross multiply by putting this over 1 and then multiplying, cross multiplying, and we'll get negative 2.5 times 11 equals x minus 68. So negative 2.5 times 11 is negative 27.5 equals x minus 68. So then negative 27.5 plus 68, if you want to get x by itself, you'd have to add 68 to both sides. You get 68 minus the 27.5 there, you're going to get 40.5. So AJ's mark was not great because he only got 40.5% on the exam. Question 5. It says the heights of 5-year-olds entering kindergarten are normally distributed with a mean of 114 centimeters. And Lily's height is 111 centimeters, which is 1.03 standard deviations above the mean. So this piece of information here is not telling you the standard deviation. It's telling you that it's 1.03 standard deviations above the mean. So that means that the z-score is 1.03, positive 1.03. And now I think that is a mistake actually, because it should be, if she's only 111 and the mean is mean is 114, this should actually be below, not above. There's a mistake in that question. So the z-score, this case here, we'll write out what we know first. We know the data value is 111, and we know the mean is 114, and we know the z-score is negative 1.03. Okay, that's so if we fill in our formula, we know that negative 1.03 should equal, and I should write the formula out again, I suppose. Z-score is x minus mean over standard deviation. So we know that the z-score is negative 1.03. We know that the data value is 111 minus 114 is the mean over the standard deviation we don't know. That's what we're looking for. So to solve this now, we've got negative 1.03 equals negative 3 over the standard deviation. It's a pretty sad looking standard deviation symbol, isn't it? Try again. So now we can basically either put this over 1 and cross multiply, or multiply both sides by the standard deviation to get rid of the fraction. So either way, if you cross multiply, most people like cross multiplying, that would be negative 1.03 times the standard deviation equals negative 3 times 1, which would just be negative 3. And then to get the standard deviation by itself, we would have to divide both sides by negative 1.03. And that gives us 2.9. 1, 2, 6, so on. So we round that off to 2 decimal places. That would be 2.91. So the next question says the mean mark on a public exam was 54% with a standard deviation of 14. The exam was determined to be too difficult and the Department of Education decided to adjust the original marks by raising the mean to 62% while reducing the standard deviation to 10 and leaving the z-scores unchanged. I'm assuming that's 10%. Determine the new mark for a student who received an original mark of 45%. So right now we have to look at, I said that the z-score remained unchanged, so first we have to do is find the original z-score with the original data before they made any changes. So the original z-score would be z equals data value minus the mean over the standard deviation. And this would be the z-score. For the first piece, the first mark was original mark was 45, and the mean was 54, and the standard deviation was 14. So when we work that out, we get negative 9 divided by 14 is negative 0.64, 2 decimal places, 642, 8, so on, da da da. So that would be to 2 decimal places, that would be negative 0.64. So then when they made the adjustments, so the new, it says what would the new mark be? So the new mark, if we're looking for that, we would know that the z-score is still going to use the z-score formula with the new data. I should say the new data, not the new mark there, because we're going to find the new mark, but it's new data. We have x minus mean over the standard deviation, and the z-score is not going to change, so the z-score would still be negative 0.64. We don't know the new data value, but we do know the mean has been raised to 62 now, and we do know that the standard deviation has been reduced to a 10. So if we go to solve this, we can put this over 1 and cross multiply, or multiply both sides by 10 to get rid of the fraction. Either way you're going to get x minus 62 equals 10 times negative 0.64, which is x minus 62 equals negative 6.4. And then to get x by itself, you want to add 62 to both sides, so you get negative 6.4 plus 62, which is 55.6. So in this case, the student who originally failed would now be passing with a mark of 55.6%. So that's the end of that part of the section, the first part of section 5.5, and there's some questions there, 1, 5, and 10, and page 292 of the text that you can try, and I do have a worksheet that I can pass out as well.